So today we are going to get started with a very interesting chapter, what is called as fins, that is heat transfer from extended surfaces. Surfaces are extended and they are also called as fins. So the objectives are studying the fins and the extended surfaces. So we will derive one-dimensional energy equation for this extended surfaces. So where do we use these fins? If you just take any scooter, you can see that the IC engine is cooled through using these fins. These are the fins. Any pump if you take, the motor is cooled by these fins. So if you take any heat exchanger, air cooled heat exchanger, so in this there are fins. You can see that there are fins on the aluminum tubes and the copper tubes in the air cooled heat exchanger. Okay. So fins are used to increase the heat transfer. Why are they used? And they are also used in computer applications. You can see that these are the aluminum fins, these are the copper fins. So they are there, and you can see that there is a fin and there is a fan over that. So all these applications suggest that fins are being used in various thermal management applications in various situations. So why does one need a fin? So to understand that, so this is a scenario where you have a base surface where there is no fin, and now these are the fins which you have put, that is you have extended the surface by extra material. So why does this necessity come? So let us study, let us write down the heading as extended surfaces, or fins. So here, if I have to take away from a base surface, Q convection is equal to H into area into Ts minus T infinity, where H is the heat transfer coefficient, area is the area from which the heat transfer is taking place, Ts is the surface temperature, T infinity is the ambient temperature or the fluid temperature. So you want to always maximize Q dot convection, you want to increase this. There is one way to increase is increase the H. For this you have to use either fan or a pump which will involve pumping power. So that requires investment of pumping power. Or you can decrease Ts, you do not have control, that is what you want to decrease. Ts, T infinity you want to decrease, that can be done by either a refrigerator or a chiller, but then for that again you need pumping power. So both of them are active methods where you need power consumption, but there is another simple method where you can increase the area. That is what we are doing here. We increase the area by extending the surface. So this is the one time investment, there is no active, it is not active, so it does not consume the power. Now let us see where all we use this. So we can see that there are several applications, as I have told. It is used in cooling engine heads of motorcycles, lawn mowers, cooling electrical power transformers. Okay. So in air conditioners they are used. So these are typical, you can see that these are circular pin fins. Okay. So these are the typical fins which are used in various applications. So now there are various factors involved in the choice of the fins, where space, weight, manufacturing cost, all these affect the choice of the fins. Now there are various different configurations of the fins. So you can see that the fins come in various shapes, here rectangular, triangular, circular, this is of trapezoidal. So it is of decreasing area, okay, cross sectional area. So pin fins need not be of constant cross section, they can be of the various varying cross section as well. So what we are going to do in the next few minutes is that we will do a general conduction analysis of the extended surface. That is, we will assume that we will take a fin whose area is varying with x, and we will do the energy balance. But before we do that energy balance, so let us state the, so let us write the conduction analysis of extended surface. Conduction analysis of extended surface. That is, I take an extended surface and this is the area, okay, and I consider an elemental area of, this is the element I am considering. If I blow that elemental area, it looks something like this, okay, and the elemental area is having cross sectional area ACX, and this is having surface area DAS, okay, and the heat transfer is entering the heat transfer is Qx, and the heat conducted out is Qx plus dx. At the same time, it loses the heat by dq convection as well, dq convection over the length dx. So before we do the energy balance, what are the assumptions involved? So we assume steady state, that is nothing is changing, steady state conduction, that means temperature is only a function of, it is function of x, its thermal conductivity is constant, okay, and the radiation, there can be heat transfer from the fin to the atmosphere by radiation, but I am neglecting radiation from the surface is neglected, and convective heat transfer coefficient is assumed to be uniform everywhere, uniform over the surface, which may not be true in all the time, but we are assuming that we are taking the heat transfer coefficient as constant. So if you apply the energy balance, so it is, there is no energy generation, there is no energy stored, it will be E dot in equal to E dot out, that is Qx equal to Qx plus dx, this is in, this is out, and it is also losing by convection, that is plus dq convection, dq convection. So Qx is equal to, this can be written as Qx plus dou Qx by dou x into dx plus, you can write this as ordinary derivative because this is function of x only, dqx by dx plus dq convection. So this qx gets cancelled out, and qx I can replace for qx d by dx of qx is nothing but minus kac dt by dx into dx plus h das into T minus T infinity by Newton's law of cooling. This is equal to 0. Okay. So if I expand this, so, and that is if k is constant, so I can pull it out, is equal into AC into dt by dx and divided by kdx. I am dividing it by kac, kdx if I divide, plus h das, h by k das by dx into t minus t infinity equal to 0. Now if I expand this, I get d square t by dx squared and I am dividing it by AC also, plus 1 by AC into dt dAc by dx into dt by dx plus h by, so this is actually minus because this becomes minus, so this is minus h by KAC into DAS by dx into t minus t infinity equal to 0. Okay. But now most of the times we do not consider the non-uniform areas. So, most of our fins are of uniform area. If you just take this, you see this rectangular fin, the AC is not varying with x, it is having a perimeter of 2w plus 2t, cross sectional area is w into t. Here perimeter is pi d for circular fin and cross sectional area is pi d squared by 4. If that is the case, if AC is constant in both these cases, AC is not a function of x, then in that case dAc by dx becomes 0. So, in that case dAc, if my dAc by dx becomes 0 if for constant cross section, and AS equal to P into x. So, dAs by dx becomes P. So, if we substitute these two and we are left with a simple equation, that is d squared t by dx squared minus hp by KAC into t minus t infinity equal to 0. So, if I replace theta of x as t minus t infinity, okay, so then I can write this as d squared theta by dx squared. Remember, t infinity is constant, that is why I am getting d squared theta by dx squared, and I write hp by KAC as m squared. So, minus m squared theta equal to 0. This is a second order linear homogeneous differential equation. Second order differential equation. So, what we know from maths that the solution of this equation is nothing but theta equal to C1 e to the power of mx plus C2 e to the power of minus mx. To get these two constants, C1s, where C1 and C2 are constants. To get these constants, we need to have the two boundary conditions. We need to have two boundary conditions. So, how do we get that? One of the boundary conditions, this is very important. One of the boundary conditions, that is at x equal to 0, we take that as T equal to Tb, that is the base temperature is taken as constant, simply because whether your application is, whether it is your IC engine or your computer chip or your motor pumps motor, you want to keep your base temperature below a certain temperature, design temperature. For example, your chip will not work better if your temperature is above 30 degrees Celsius. So, you want to keep it always below 30. That means you are designing your fin such that your base temperature is fixed. But now the boundary condition at x equal to L can be of different boundary conditions. We consider nearly 4 boundary conditions. There can be plenty, but we are considering here 4 boundary conditions. One is convective heat transfer from the fin tip. Next is adiabatic condition at the fin tip, that means there is no heat transfer at x equal to L, and here this is at x equal to L there is heat transfer by convection, or a prescribed temperature maintained at the fin tip, that means fin tip also should not exceed certain temperature, or very long fin I am taking, infinite fin. So infinite doesn't mean really infinite. So let us take up one of the simplest. So what I will do is, let us get started with infinite fin. So in case of infinite fin, let's go to infinite fin. So in case of infinite fin, in each case, what is that I am want to do is, I want to get the temperature distribution. So if I take infinite fin, very long fin, if I take, that means at x equal to 0, t equal to Tb means theta b is equal to Tb minus T infinity. My theta becomes, this is the theta becomes Tb minus T infinity, and as x tends to infinity, T will tend to T infinity, or T will become equal to T infinity. T will become equal to T infinity. That is, so you get, if it is T infinity, then theta becomes equal to T infinity minus T infinity, that is equal to 0. So now if I substitute this in my equation, C1 e to the power of mx plus C2 e to the power of minus mx. At x equal to 0, that is theta b equal to C1 e to the power of 0 plus C2 e to the power of minus 0. That means theta b equal to C1 plus C2. And the other boundary condition is theta at tending to infinity is equal to 0 is equal to C1 e to the power of infinity plus C2 e to the power of minus infinity. Okay. So this can be written as C0 C1 e to the power of infinity plus C2 divided by e to the power of infinity. So 1 by infinity is very large, so that means this can be neglected. So you get C1 equal to 0. So if I substitute this C1 equal to 0, so then into this equation, so I get C2 equal to theta b. So if I substitute C1 and C2, I get theta equal to theta b into e to the power of minus mx. So this is my temperature distribution, that is T of x minus T infinity is equal to Tb minus T infinity into e to the power of minus mx. That means the temperature is falling exponentially. Now next thing to find out is the Q fin. How much is the heat transfer rate? As an engineer, that's what I am interested in. Not only the temperature, I want to make sure that the temperature doesn't exceed the design temperature, but at the same time there should be maximum heat transfer which is taking place. So that can be obtained by KAC dt by dx by Fourier law. You can put that at x equal to 0. So now you have theta or minus KAC d theta by dx at x equal to 0. And theta you have just now found, theta equal to theta b into e to the power of minus mx. So if you differentiate this, you get minus KAC into minus theta b into m e to the power of minus mx at x equal to 0. So you get KAC into theta b e to the power of minus 0 is 1, and recall m squared equal to hp by KAC. So m will become equal to square root of hp by KAC. So Q fin equal to square root of hp KAC into Tb minus T infinity is what is the heat transfer rate which is occurring from my fin. So this is the temperature distribution for infinite fin, and this is for the heat transfer rate. Now what we will do is, we will take up next case where it is adiabatic condition at the fin tip. Adiabatic condition, adiabatic. condition at the fin tip. Adiabatic condition at the fin tip. So, you have the same temperature, that is theta of x equal to C1 e to the power of mx plus C2 e to the power of minus mx. That, and theta, remember that it is T of x minus T infinity. Okay. And one of the conditions, theta of 0 is equal to theta b, and it is adiabatic at the fin tip, that is dt by dx at x equal to 0 is 0. That means d theta by dx at x equal to, not at x equal to L is 0. This is at the fin tip. So, now you have two equations and two unknowns. So, we should solve them and get. So, if you invoke this, you get theta b equal to C1 e to the power of 0 is 0, e to the power of 0 is 1 plus C2 e to the power of minus 0 is 1. So, this is one equation you get. The another equation, if you differentiate this from here, d theta by dx at x equal to L is 0, C1 into x e to the power of mx plus C2 into minus m e to the power of minus mx. Here instead of x, actually I am doing at a condition L. So, I differentiated and substituted for x as L. So, m, so here actually I missed out one term, that is m. Okay. So, m not x, m C1 m e to the power of ml minus m C2 e to the power of minus ml. So, what is that? I can m gets cancelled out. So, I can write C2 equal to C1 into e to the power of 2ml. So, if I substitute this here, so I get C1 equal to C1 plus C1 into e to the power of 2ml equal to theta b. So, C1 equal to theta b divided by 1 plus e to the power of 2ml. So, if I substitute C1 and C2, theta of x equal to theta b by 1 plus e to the power of 2ml e to the power of mx. Now, C2 can be written as C2 equal to C1, that is theta b from here e to the power of 2ml divided by 1 plus e to the power of 2ml. So, I can substitute this as theta b e to the power of 2ml divided by 1 plus e to the power of 2ml e to the power of minus mx. Okay. So, the algebra I will just show you here. Yeah. So, this is where we just stopped. So, you got e to the power of mx. So, this is the equation what you have gotten. So, what I do here is I just multiply and divide by e to the power of minus ml and divide by minus ml here. Here also multiply and divide by e to the power of minus ml. So, the numerator becomes e to the power of minus ml minus x, and denominator becomes e to the power of minus ml plus e to the power of ml. Here in the numerator it becomes e to the power of ml minus x, because 2 ml and minus ml becomes ml. So, you have e to the power of minus ml minus x plus e to the power of ml minus x upon e to the power of minus ml plus e to the power of ml. We know that cos hyperbolic x is e to the power of x plus e to the power of minus x by 2. So, if you substitute this here, so you get in the numerator cos hyperbolic ml minus x and denominator cos hyperbolic ml. So, let us write that as theta of x is theta of x by theta b is equal to cos hyperbolic m of L minus x upon cos hyperbolic ml. That is nothing but t of x minus t infinity divided by tb minus t infinity. Now, I need to get the heat transfer rate. So, Q equal to minus KAC d theta by dx at x equal to 0. Now, I have already this. So, if I just differentiate this, minus KAC into theta b into, if I differentiate cos hyperbolic, I get minus m sin hyperbolic m of L minus x upon cos hyperbolic ml. Now, this is at x equal to 0. So, if you substitute this x equal to 0, you are left with sin hyperbolic ml divided by cos hyperbolic ml, minus into minus becomes plus, and m is equal to square root of hp by kac. So, this kac and this kac will get subsumed into the square root. So, you get hpkac into theta b into tan hyperbolic ml. So, this is the temperature distribution, this is the heat transfer rate what you are going to get. So, here theta b is nothing but Tb minus T infinity into square root of Hp KAC into tan hyperbolic ml. So, that is the heat transfer rate what you get for adiabatic condition. So, you got the temperature distribution for the adiabatic fin tip, and also you got the heat transfer rate from these equations. Now, let us take up the next case, that is the temperature, the prescribed temperature at the fin tip. So, that is, let us write the prescribed temperature at the fin tip. At the fin tip, that is, you have theta of x equal to C1 e to the power of mx plus C2 e to the power of minus mx, and you know theta of x equal to T of x minus T infinity. Now, prescribed temperature theta at x equal to 0 is theta b, and theta at x equal to L is theta L, okay, theta L, not theta b, theta L. So, I have theta of 0, which implies that theta b is equal to C1 plus C2 from the above equation, and theta L is equal to C1 e to the power of ml plus theta b minus C1 into e to the power of minus ml. Okay, theta b minus C1 into e to the power of minus ml. So, now what we will do is, I will not do this algebra. If you just go and see this at the prescribed temperature, yeah. So, this is the equations which we just wrote. Now, if you substitute for C2 from here theta b minus C1, if you just substitute theta b minus C1 and theta L becomes this and do the algebra, you get C1 equal to theta L minus theta b blah 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 blah. So, now this C1, if you substitute here, you get C2. So, you got C1 and C2, and here C2 I have just done the algebra, just taken the LCM and gotten this. So, you got the C1 and C2. If you substitute this C1 and C2, now substitute this and do the whole of this algebra, again you end up getting theta L equal to theta x is equal to theta L by theta b sin hyperbolic mx plus sin hyperbolic ml minus x by sin hyperbolic ml. So, where again m is equal to square root of hp by kac. So, now if you take the temperature heat transfer rate, that is q equal to minus kac dt by dx at x equal to 0, that is nothing but d theta by dx at x equal to 0, but I have gotten the temperature distribution this. So, if you differentiate that, sin hyperbolic mx becomes m cos hyperbolic mx and theta b here m theta b cos hyperbolic ml minus x, and you have sin hyperbolic ml. So you get here KAC cos hyperbolic, if you just substitute x equal to 0, so you get this becomes m theta b and this is m theta l. So this m minus sign is subsumed inside. So if you just do the algebra, you get q equal to square root of HPKAC theta b cos hyperbolic ml minus theta l divided by sin hyperbolic ml. So like that, you can do the other way also. If you don't want to do cos hyperbolic, you can just substitute in terms of e to the power of and get that done. So summary is that we just did adiabatic condition where we got the temperature distribution and the fin heat transfer rate. For prescribed temperature, we just now got this temperature distribution and the heat transfer rate, and infinitely long it's going to be very exponential temperature distribution, and the fin heat transfer rate is theta b into square root of HPKAC. So in the next class what we will do is we will try to cover this convective heat transfer. I am not going to do the complete algebra, but I will just show you the salient steps, and the most important of this is the next is what should be the length of the fin. That is what we are going to understand in the next class. Thank you.